This is Enceladus, Saturn's sixth largest moon, a tiny world orbiting a giant planet. But don't let its seemingly unimpressive size fool you. When the Cassini space probe found huge cryovolcanic plumes erupting from its south pole, this little world brought the entire scientific community to a standstill. What was going on? Flying through these icy jets got us closer to an answer. The probe discovered water, organic molecules, and hints of a hidden ocean filled with hydrothermal vents. But in 2017, Cassini ran out of fuel. As it dived into Saturn, it took with it our only means of probing Enceladus, leaving us with countless unanswered questions. Does it have a global ocean? What exactly is happening below the surface? And most importantly, could it be home to life? A decade on, we've not yet returned to Enceladus, but the science hasn't stopped. The James Webb Space Telescope has turned its attention to the moon, and researchers are still mining the data that Cassini sent back. And luckily, we found more answers than you might think. I'm McColgan, and you're watching Astrum. Join me today as we return to this surprise in the Saturn system, explore the incredible chemical complexity hiding below its surface, and reveal how 10-year-old data is still shocking us, all in the search for life beyond Earth. At just 500 kilometers across, Enceladus is a tiny world. It's similar in size to the state of Arizona. It orbits 238,000 kilometers from Saturn, where the Sun is a mere distant spark, and surface temperatures average a bone-chilling minus 201 degrees Celsius. All these factors make Enceladus an incredibly difficult target to track. It was finally discovered by Sir William Herschel in 1789, and to spot it required the largest telescope the world had ever seen. The instrument, built by Herschel and his sister Caroline, was so pioneering that its half-ton mirror required more than a year of painstaking polishing. Yet, even through this behemoth scope, Enceladus looked like nothing more than an unremarkable, icy rock. Herschel's telescope was so far ahead of its time that this remained our only perspective of the Saturnian satellite for nearly 200 years. It wasn't until the 1980s, when Voyager 1 and 2 performed their swift flybys, that our perspective shifted forever. The images sent back didn't show the featureless world we expected, but instead revealed regions that were remarkably smooth and crater-free, suggesting the moon had been recently seismically active. Most curiously, Enceladus was found sitting directly in the densest part of Saturn's E-ring, leading scientists to suspect the moon was somehow feeding the ring with material. Was Enceladus alive? The mysteries raised by the Voyager flybys made Enceladus a high priority target for a follow-up, and directly fueled the planning of the Cassini-Huygens mission. The Titan 4B rocket launched Cassini in 1997, and in late 2004, 6 years after its double slingshot maneuver around Venus, it reached Saturn to carry on Voyager's legacy. It was a monumental effort that has since generated more than 4,000 scientific papers, but no discovery caused more hype than the events of early 2005. During its first flybys, Cassini's cameras caught sight of massive geysers erupting from Enceladus into the vacuum of space. These vents were ejecting 250 kilograms of water and ice every second at speeds of over 1,000 kilometers per hour. This confirmed it. Enceladus had an atmosphere and active geology. NASA immediately shifted the mission's course, ordering Cassini to perform a maverick maneuver, passing just 50 kilometers above the surface to taste the plumes. What was worth such a risk, you might ask? Well, NASA were looking for signs of extraterrestrial life. And I for one can't wait to find out for sure if alien life exists elsewhere in the universe. And it amazes me every day that humanity now has the technology and ability to look for it. That kind of tech doesn't just appear out of nowhere. It takes years of learning maths and coding to create the programs that run probes like Cassini. If you are a student who's serious about studying maths and coding, you should check out Brilliant, today's sponsor. I tried their probability and chance course. I want to figure out the odds of alien life existing after all. And I found their team of MIT, Stanford and Harvard teachers made a course filled with thought-provoking and brain-teasing challenges. Because every lesson is interactive and breaks down the concepts step by step, it's like having your own personal tutor. Brilliant is suitable for all ages, 10 to 110. Whether you're learning yourself or hoping to inspire young minds by dividing maths and coding with your kids, their comprehensive curriculum lets you go as far and as fast as you like. So if you're looking to excel at a new field of knowledge, why not scan my QR code or click the link brilliant.org/Astrum in the description below. Doing so will give you 20% off an annual premium subscription for unlimited daily access to all Brilliant has on offer. Now, back to that radical Cassini maneuver. A major motivator of our exploration of space is the hope that we're not alone. To define life, NASA looks for a self-sustaining chemical system capable of Darwinian evolution. But what does that mean when we are searching on Enceladus? Well, there are 4 boxes we need to check: liquid water, energy, chemicals, and time. First up, liquid water, the solvent of life. The question here isn't whether Enceladus has it, that's abundantly clear, but rather we need to ask how much water is there and where is it coming from? Cassini's initial photos and infrared images from 2006 showed significant heat at the South Pole. This incredible photo shows the famous tiger stripes, long fissures in the icy crust, hinting at the activity below. And clearly some form of a liquid ocean exists here, potentially with hydrothermal activity that powers the huge ice plumes. For years, scientists believed this ocean was small and lens-shaped. However, by meticulously tracking surface features over 7 years, they noticed the moon librates, or wobbles, a lot more than would be possible with just a small polar ocean. This finding led to an astonishing realization. The core isn't rigidly connected to the surface. We are now confident that the ocean covers the rocky core across its entire surface. In 2025, there was another breakthrough. Scientists from the University of Oxford, Southwest Research Institute and the Planetary Science Institute looked back through the Cassini observations of the North Pole from its winter in 2005 and summer in 2015. They found that not only was heat escaping at the South Pole, but also at the North Pole. It was 7 degrees warmer than they expected. This result tells us that Enceladus is generating a lot more internal heat than we thought, and suggests the ocean may have been there for a while. But this far from the sun, it is bitterly cold. As I mentioned, the surface temperature of Enceladus is minus 201 degrees Celsius. There is no way water should be liquid. So, next on the list for scientists to check out was energy. Where was the heat coming from? If Enceladus generated heat by radioactive decay in its core, like Earth does, the energy produced would only be 1% of what Cassini was witnessing. So in 2017, a team led by Gail Schoble proposed a solution. Enceladus is tidally locked to Saturn, meaning the moon only ever shows one face to the planet. This distorts Enceladus, which creates heat inside the moon through internal friction and powers geological activity. But it's not enough to just generate and radiate the heat. It needs to be physically transported from the core to the ocean above. How? Well, incredibly, It seems that water perfuses the silicate mineral core where it is heated, causing it to rise in focused plumes that pepper the seafloor around the South Pole. In 2022, a study led by Wanying Kan found further proof of these vents. Based on Cassini's data, they created models of Enceladus's icy surface to try and work out the salinity of the ocean. They found that it's just a little less salty than we find here on Earth, and that means that there must be, or have been, water-rock reactions, or in other words, vents, at some point. Hydrothermal vents are credited by scientists as powering the origin of life on Earth. That these vents may also exist on a small moon around a gas giant is an electrifying discovery, because they give us the third requirement for life: chemicals. Cassini was equipped with a mass spectrometer, an instrument that can identify individual molecules by the mass of their ions. On its flybys, it detected hydrogen, believed to be a fuel source for early life, and complicated hydrocarbons containing oxygen, carbon, and nitrogen. But scientists racing to process the huge volume and richness of data couldn't keep up. Before they could get through it all, the Cassini mission came to an end, and on the 15th of September 2017, it was sent hurtling towards Saturn and was vaporized by the planet's atmosphere, in a self-destructive maneuver designed to protect potential habitable life on Enceladus and Titan from contamination by Earth-borne microbes. Though Cassini's mission had been completed, ours had not. An analysis in 2018 had confirmed the existence of ring-shaped organic molecules and simple oxygen-containing molecules, indicating some limited chemistry was occurring. Another huge boost to the search for life came in 2022, when the last element crucial to life was observed in the data: phosphorus. With its discovery, we now had all 6 main elements believed to be necessary for life: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, which scientists know by the acronym CHNOPS. For a while, this felt like the end of the story, but it turns out this particular book had a few more chapters to go. When scientists first saw the mass spec data from Cassini, they weren't confident in what they were looking at. It turns out that the spectra of a carefully prepared sample, analyzed while stationary in a lab, looks somewhat different to the one obtained by crashing the detector into a ejector at 64,000 km per hour in space. A mass spectrum analyzer works by ionizing and breaking a molecule apart at high energy. How the molecule breaks apart matters. A molecule's fingerprint can look different depending on how it was fragmented, in the same way that a watermelon prepared with a knife looks different from one prepared with a blender. By understanding the typical pattern of how an object breaks under certain conditions, we can be more confident of what it used to be. Improved analytical tools helped a team, led by Nozea Kavaja from the Institute of Space Systems in Stuttgart, do exactly that. After more than a decade of studying the plume flybys, Kawaja's team published their results last year, using samples that were collected when Cassini passed just 20 kilometers from the moon's surface. Unlike others the probe collected, they were just minutes old, and therefore unchanged by ionizing radiation from the sun like other particles in the E-ring. These samples were a pristine example of what's in the oceans of Enceladus. In the most extreme examples, they found molecules more closely related to life than ever before: carbon dioxide, carbon-rich alkanes and alkenes, cyclic esters and ethers, ethyls, and other nitrogen and oxygen-bearing compounds. In other words, complex chemistry, potentially powered by hydrothermal vents. These molecules are the Lego blocks of chemistry. More functional groups allow for more complex reactions. In a lab, these can become so complex that they even demonstrate Darwinian evolution. And once you have evolution, there's just one last requirement: time. What we need to know is, how stable and frequent is this geothermal activity? Would life have had enough time to emerge on Enceladus? Although Cassini was at Saturn for 13 years, that was, of course, too short a time to be conclusive. Enter the James Webb Space Telescope. A team led by Dr. Jerónimo Villanueva used 10 hours of the James Webb's time to check in on Enceladus, and what they saw was shocking. The moon had an even more enormous plume erupting from its south pole, expanding to 20 times the size of the moon itself. That is significantly larger than what Cassini saw. These observations widened the known window of Enceladus' activity, and they solved another massive mystery. Where does Saturn's atmospheric water come from? The images show that Enceladus feeds a large torus of ice particles around Saturn, making it the only moon in the solar system that affects the atmospheric chemistry of its host planet. But these water ice particles also have another impact on the planet. As they travel through the Saturn system, they're stripped of electrons, becoming ionized. This then creates an electrically charged plasma, which scientists have recently discovered interacts with the planet's magnetic field. Plasma waves 504,000 kilometers long, that's 1,000 times the moon's diameter, known as the Alpenwings, stream from the moon. The main ones go from Enceladus to the planet, but others are reflected back, creating an intriguing lattice of plasma around Saturn. We still don't fully understand them, but they're a surprising consequence of Enceladus' great geysers. But how long will this activity last? Within the last year, decade-old data from the Cassini composite infrared spectrometer was compared to models of Enceladus' surface temperature. The team, comprising Georgina Miles and Carly Howitt, were able to show that the total thermal output from the surface is very well matched with the predicted heat generation in the core. This suggests the moon's current ocean epoch will be long-lived, and that it is exactly what life needs to emerge. It is incredible how much more has been learned simply from reanalyzing old Cassini data with new techniques. And it's not just the professionals who are making discoveries. In 2017, amateur astronomer Ted Strike looked back at old Voyager images of Enceladus and found a feature that could have changed the course of the original Cassini mission: a water plume. Can you spot it? If we had known about it when the mission was in planning, how different might the design of Cassini been? Well, whatever changes scientists and engineers might have made, they now have a chance to be realized as new missions are being planned to continue the work of Cassini. The European Space Agency is racing forward with a mission set to launch in 2042, to arrive at Saturn in 2053 with a potential landing on Enceladus in 2058. We already know Enceladus has all the conditions to kickstart life, so it's exciting to think, what will we be able to find when we look below the ice? Fortunately, we won't have to wait quite that long to get some answers on life on icy moons generally. Another ESA mission called JWST, or Jupiter Icy Moons Explorer, is already on its way and expected to arrive at Jupiter in 2031 to study Callisto, Europa, and Ganymede. Its mission purpose is to investigate the emergence of habitable worlds around gas giants. Two other proposed missions will explore Saturn's moons in new ways. The Dragonfly mission to Titan will take advantage of the thick nitrogen atmosphere and use a drone for the first time on a natural satellite. Outside of the national space agencies, a privately funded mission called Breakthrough Enceladus is also planned, though currently this project appears to be dormant. But the mission I'm most excited about is the Enceladus Explorer, a project funded by the German Aerospace Center that proposes to send a nuclear ice mole, yes, you heard that correctly, to melt its way deep into the crust and expose untouched niches within the ice to search for life. If any of these even hint that proto-life processes are active on an object outside the usual habitable zone, we will have opened up a whole new realm of possible places life could take hold across the galaxy. Maybe life isn't rare after all. I'm always reminded of a fantastic line from Jeremy England. You start with a random clump of atoms, and if you shine a light on it for long enough, it should not be so surprising that you get a plant. Perhaps scientists didn't see those plumes on the original Voyager images because they simply weren't expecting to see them. But now that we know what we're looking for, there is no doubt more discoveries are on the way. There is also almost certainly yet more to find within Cassini's data even now, a decade after its mission ended in spectacular style. And I am as excited now as I was in 2004, when the probe first reached Saturn and its moons. If you've ever watched an Astrum video and found yourself pausing just to take in the beauty of space, you're not alone. The colours, the motion, the scale, they remind us how vast and awe-inspiring the universe really is. Have you ever had your breath taken away when seeing these videos of our Sun, Milky Way, or perhaps Venus? Well, now, Patreon members have access to these wallpapers for your phone and laptop. Sign up with the link below. It's a simple way to bring that sense of wonder into your daily life while supporting future Astrum creations.